As you're learning how to program, it helps to have a sense of where your work fits into the bigger picture. How is it that the code and the programs you write are able to run on your machine? Well, this is a pretty deep subject. So in this video, we're going to take a brief introduction to the primary components and the layers of a computing system. And we're going to look specifically at these four things. First, we're going to look at user space processes. These are the apps that you know and love, right? And when you're writing programs, you're going to be writing little apps that run as a user space process on your system. Then we're going to take a look at, well, how is it that we start apps and how do we close them and control them? That's what we call the shell. We think of this as part of our operating system, but we'll learn that there's a little bit more nuance than that. There's also something in our operating system called the kernel. It's responsible for fairly sharing the resources of your machine. Together, these two components are what you would probably think of as an operating system. But it helps to distinguish these two things because we'll be looking at a different kind of shell in this course and as you learn how to program than you're used to interacting with. And lastly, we're going to take a look at what are some of the primary components of hardware. This is what you think of as your device. So the phone or the laptop that you're holding is hardware. And all of the things that we listed before run on top of our hardware, right? Your operating system, your programs are all made possible because the machine that you're using is able to run them and keep track of all of the state that they have as part of their operations. So let's dive right in and focus first on what it is that you'll be concerned with in this course, which is user space processes. These are the running apps of your machine. These apps might be visible or invisible, right? So we know that there are visible apps that you're interacting with from time to time. And those apps are things like the web browser that you're using to watch this video in, or the YouTube app, perhaps, or when you're running Word or any other application on your phone, it might be visible at some time. But you also know that behind the scenes, there can be other applications running as well, such as maybe you use Dropbox for backing things up, or some security software that's checking your files in the background that you're not interacting with, but you know that they're still running and they're still doing things on your behalf. When you switch out of applications or minimize them, you know that they're keeping track of where they were so that you can come back to them later. We think of that idea as state. So processes are programs in motion. And what I mean by in motion is that they're running. They are actively being evaluated on your machine. They have state associated with them. And we'll talk a little bit more about what we mean by state more precisely and specifically in just a moment. These are things like, Office, Chrome, your web browser, Instagram, and so on. These are also the applications that you write. So your work, when it runs, is going to be a user space process. And we'll see that that means we need to be able to start these. You need to be able to begin running the programs that you write. We probably need a way of being able to stop these. And so how is it that we can start and stop programs? Well, you're used to doing this by now. Through what you think of as your operating system, but we're going to call a little bit more specifically a shell. And in this course, we're going to look at what's called a command line interface, which is a slightly different type of shell than you're used to. Before we talk about a command line interface, let's talk about what a shell is generally. It is a program for starting, stopping, and otherwise controlling your running processes, right? So when you interact with your phone or your computer and you start a program that begins a process, when you click the icon for that application and it starts it up, your shell is what you're interacting with to start it up. You're used to using, for the most part, graphical user interface shells. So some examples of graphical, I'm not going to write this out. The common acronym here is graphical user interface, GUI. Examples are, your iOS interface, your Android interface, Windows, and Mac OS, and other types of user interfaces that you can begin programs from are examples of graphical user interface shells. Well, it turns out there's another popular kind of shell, which is a little bit older than a graphical user interface shell, which is a text-driven shell or a textual shell. And we call these command line interfaces. And you'll commonly see this abbreviated as CLI. So if you see the letters CLI, know that that's short for command line interface. And these are shells, just the same as what you're clicking on and interacting with when you're working on starting up a program on your phone. But instead of clicking on things, we'll be typing in commands. And textual interfaces are really powerful. They can do some things that we couldn't actually do very easily with graphical user interfaces. And in the professional software engineering and data science worlds, having proficiency in navigating your computer using a textual command line shell that allows you to start and stop and control your programs from it is a superpower. And you'll have quite a lot of capabilities as we get into this course and as you expand your command line interface shell fluency. You can do a number of incredibly cool things. Our textual shells tend to run in what we call the terminal. I'm going to make a note of this because in the terminal, that's the name of the program that's sort of giving you the access to the command line shell, right? And in our code editor, VS Code, we'll be using a terminal to interact with our shell that then begins our programs. Well, you are perhaps wondering, how is it that a shell can begin a program? What does it depend upon? Well, the shell is interacting with something called a kernel. And these words are related. If you think about, the kernel of a seed, it's protected by typically some kind of outer shell. So the shell is offering some protection and making it easier for us to interact with the kernel. The kernel, its job is to fairly share the resources of our machines. As you know, you can run many different programs at the same time. You can have many running processes. And you don't want one of those programs to hog all of the resources so that your other programs can't run. The operating system is responsible for figuring out, well, how much time should I give to a certain program? How many resources should I give? How much of my memory should I give? And those resources are what we'll talk about next. They're the hardware. But before we get there, it's worth mentioning that the operating system also provides protection between processes. So it protects processes from one another. The exact mechanisms for how it does this are a little bit beyond our concerns, but it has some facilities that allow us, as someone writing a process, to not have to worry about all of the other things that might be running on our phone. This is great because when you install more programs or apps, you don't want them to potentially break the other things that you have on your machine. You kind of want them to be isolated from one another. You also want them to be able to interact at times, right? You want to be able to take that photo from your camera application and share it through Instagram. And the operating system can help facilitate some of those the communications between processes, but primarily it's focused on how do we insulate them and protect them from one another. Well, what are these resources we're talking about, and what is it that the operating system is actually controlling? Well, the operating system is responsible for managing our hardware. So the hardware is the actual machine, the electronic circuitry that you can touch and feel and has a physical presence. And for our parts, we're going to be thinking about sort of three components of hardware. The CPU is the central processing unit. And this is what is often called the brains of a computer. But it's not actually that smart. The central processing unit is responsible for carrying out instructions, and it has a very limited set of instructions that it can carry out, but it can do so incredibly fast at billions of instructions per second. Things like add two numbers, store one number in memory, keep track of something else. It's very, very fast, but it's quite limited in what it can do. It's sort of a sleight of hand. It almost feels like magic that we can carry out the amazing things that we can in our applications, such as photo filters and editing videos and things like that, using such simple instructions that a computer actually has built into it. But that's the magic of computer science. And because these machines are able to operate so fast, billions of operations per second, we can do quite a bit of work by being clever about how we organize the instructions we give it. And that's what programming is all about. So the CPU is responsible for carrying out instructions like arithmetic and other simple instructions, and storing the results of those instructions in memory. Memory winds up being the more important component of our hardware. And we think of memory, when I use memory in this course and more generally, I'm going to be thinking of this as an ephemeral memory. So it's short term. By short term, I mean what we store in memory won't exist anymore if we turn off our phone or our device. If we start up a program and we store some information in memory, we stop that program and start it back up again, it also wouldn't be there. And I'll talk a little bit more about that distinction in just a moment. But it's very fast. And as computer programmers in our time, we have access to billions of cells of memory. Memory has become abundant. And so a modern iPhone, for example, has 2 billion or 4 billion cells of memory available to it for us to store little pieces of information in. And when we're writing programs, we're going to think quite a bit about what is it that we're storing in memory and how do we think about the organization of our program's use of memory. Once you understand that, a lot of programming becomes more digestible and easy to navigate. So if memory is ephemeral, how is it that we can save things and come back to them after restarting our phones and whatnot? Well, there's a third device component here that I'm just going to label as storage broadly, and this is long-term persistent storage. And long-term persistent storage is slower than your memory. This is why we have two different types of storage. In fact, there's more layers of types of storage that exist in your machine. But for our parts right now, these are the only two we're going to think about. And typically the trade-off is how much of it you have available to you versus how fast it is for you to be able to access it. Memory, we have a little bit less of available to us at any given time than the storage. Your storage, your 128 gigabytes, 256 gigabytes on modern machines is orders of magnitude larger than the amount of memory you have. But it's slower. So this is where you would store things like pictures, saved files, and it exists even after you close your programs and turn off your computer. It doesn't require active electricity in order to keep track of. So this is a brief introduction to our hardware. We have our central processing unit, which is going to follow our instructions. Our memory is what we're going to be concerned with storing our results and loading our data into it. And storage, if we wanted to save files such that we, read from storage in order to bring in some data to a program and then save it out so that we have reports that we can refer back to later. These are the three high-level components as we're learning how to program we're going to be concerned with. So just to bring us back up to where our focus is on user processes, the operating system kernel is responsible for managing those resources. It's figuring out, hey, okay, you want to start a program. Well, it's going to need some memory. Let me allocate some memory for you and keep track of who I've given what memory to and sort of divvy that up. So the operating system is dispatching who has what resources available to them. If you want to save a file, your operating system knows who has what users of your system have access to what files and things like that. So your operating system, when you want to actually start a program, it controls running processes. And it decides how much time of your computer, your central processing unit, to give to each of your running processes. And it's sort of responsible for making sure that your overall system feels like you can interact with it. And so if you have multiple apps running, it's what is making possible it feeling like they're all running simultaneously at the same time and one's not taking up all of the resources of the other. But if you were to interact with your operating system kernel directly, it would be very painful, right? You would need to write programs in order to do this. And so the idea of an operating system shell is, well, we want to make it easier for people to use the operating system's facilities directly. This is what gives you the ability to click on icons, or as we learn our command line interface, how we can type in commands to begin running processes and stop them and other things. The shell makes that much easier and more friendly for us to use as humans than it would if we were trying to interact with our operating system kernel directly. Now, if you were to ask someone out in the public generally, is there a difference between the buttons that you click on in iOS versus the operating system kernel itself? I think the tendency would be to think of those two things as bundled because you typically get them together. But for our purposes, it's nice to think of them as separate. And the reason for that is because it helps to know that when you're writing commands in the terminal, in a command line interface, you're doing the same kinds of things that are happening when you click on an icon of an app and start up that application. The shell says, hey, operating system, I want to start a new process, and here's the program that I want to run. And ultimately, once that program is running, that's where your code comes into play. So the user space process is where the work that we do will actually run. And for the rest of the semester, you almost don't have to think about any of what comes after this. We don't have to think about the shell too much other than what we need to know in order to start our processes. We're not going to spend any time thinking about the operating system kernel or the hardware more directly. Those things are abstracted away from us, but as you continue your computer science journey, you'll learn more about the details of each. So when we have a user space process, when it's finally time for our program to run, it's going to have some memory available to it. So I want to make a note of this. When running, it's going to take the instructions that you write, and it's going to keep track of where in the instructions it is. So where in instructions. Your instructions are just like a recipe, and your computer is going to be focused on one step of those instructions at any given time in this course. And it's going to keep track of where it is in those instructions, as well as it's going to have memory. And your instructions are going to be responsible for manipulating memory, for storing results in memory, for computing various things, for coming up with shapes if we're doing something graphical, and storing the results of that in memory. And because the operating system is keeping the memory for your program separate from other programs, we don't really have to worry about too much about what else is going on our machine. We kind of have this nice little isolated sandbox available to us when we're writing our programs. And when we start up a program, as we'll look at in the next lesson, we're going to have a clean slate, effectively, that is ours to decide what to do with and how we want to use the memory that's available to us in our program in order to achieve our program's goals. So that when your program is running, it's got instructions and it's keeping track of where in the instructions it is. It's got memory available to it, and we'll learn that the memory that's available is broken into two different segments. And we'll spend a lot of time looking at how those segments are used and what's kept track of in each of them, right? So this is a very brief introduction to the idea of computing systems. We are going to spend most of our time and energy focused on user space processes. This is where your code runs. But it's useful to know that beneath your code, there are other layers of the system. And when you start your programs, you're going to be doing so through a shell. We're going to be looking at command line interfaces and textual shells, but your graphical user interface is another example of that. Beneath that are what allow us to use our computers to run many different applications at the same time without really having to worry about it. So the quality of our operating system and our hardware is that we're able to multitask and we're able to run our programs and navigate much more complex workloads than we could, even a decade ago, through the facilities provided by these layers of our system. In the next video, we're going to look at what is it that makes up our user space processes memory, and how do we think about our instructions that we begin writing? How are they interpreted by the programming language and evaluated in the context of our machine?